Okay, so good afternoon. Firstly, any questions on design homework or previous lecture? Okay, I posted the recording on YouTube from last lecture just a few hours ago, so should be there in case you need to watch it. Also, a reminder on Friday: make sure to bring your laptops with the Logic Sim installed because we'll be going through that. So just a second reminder, no lecture on Monday. I will be announcing a makeup. So watch out on the email. Quite possibly, I might do it on uh, Thursday evening, but depending upon room availability. Otherwise, it could be later in the quarter. So just keep an eye on Piazza for that. Okay, so today's lecture we'll kind of move beyond representing digital information to how you begin to process digital information, which is really what this course is really kind of about. And again, we are still on chapter 1. So, so I talked about the notion of systems last time, namely something which takes some input, produces some output. Of course, the output represents, generally speaking, some sort of a transformed version of the input. So it does something to the input, may also rely on previous inputs which came. So we talked about the notion of memory, that is, a system may remember the inputs that came historically, and then at any given point in time, the output which is produced depends not just on the current input, but also inputs which came previously. So we had very broadly kind of a simpler type of system, namely which are memoryless, and systems which depend upon memory of the previous inputs. So combinational systems or combinational logic or more combinational logic circuits, they refer to systems where there is no memory. So output depends entirely on the current input which is being observed. So for example, you might imagine a simple system to control fan in an AC system, and what it might do is it might take reading from a temperature sensor, which has been appropriately digitized, as well as a preset temperature. So usually in thermostats, there might be there's some way for you to express what temperature you want, and kind of the idea is that I compare the current temperature against the preset temperature, and then I have a system. What it does is it checks whether input A and compares it against input B, and if A is greater than B, then it turns the fan on. So it has an output called fan on, which presumably goes on to control some electrical switch. So whenever current temperature is higher than the preset temperature, then you need to cool things down, and therefore it is going to turn the fan on. And if current temperature falls below the preset temperature, then A greater than B would be false, and very commonly false values are represented using 0 and true values using 1. So fan on would be 0 or logic 0 or false or off. So the fan would be turned off. So this is an example where fan is being turned on off depending entirely on what the current temperature is and how it compares with whatever the user preset using some sort of a keyboard or something like that. So this box, a comparison function, is an example of a combinational function, which is a memoryless function. So um, uh, nothing special about it, but this is sort of comparison is an example of a mathematical function which just depends upon the current values of the two inputs. Oh, one other thing. So you see this notation out here, kind of hash cross sign with sort of a number against it. It's very commonly used to refer to the fact that this signal has 2 bits. So this is the number of bits basically. Okay, so let me kind of. Okay. And absence of such a thing, like on the output, means it's a single bit signal. So current temperature and preset temperature are both 2-bit signals. and therefore can take up to 4 distinct values. So now let's look at what this function a greater than b would look like. So a and b, the current temperature and the preset temperature, they can both take they're 2-bit numbers. They can take 4 distinct values. So let's imagine our representation was such that on current temperature, 00 meant 50-degree temperature, 01 meant 60 degree, 10 meant 70 degree, and 11 meant 80 degrees. And for preset temperature, 00 meant 60, 01 meant 65, 10 meant 70, 11 meant 75. So this kind of corresponds to what we discussed last time, that sort of somehow we need to represent the discrete values of interest in terms of our binary values. So this is, let's say, what we chose. A few comments out here. So firstly, you would see that I'm choosing to represent, like, let's look at the temperature 60. 60, when it comes to current temperature, is being represented as 01. And 60, when it came to preset temperature, is being represented as 00. And that's perfectly fine, because current temperature is a different piece of information than the preset temperature. So these are two entirely different things. And so the fact that I have 4 values here and 4 values here is entirely coincidental. It could have been that I had 8 values of preset temperature, for example, in which case I would have had 3 bits or more bits. And the other thing is the representation may be kind of entirely different. So the same temperature is being represented using 2 very different representations out on this side. So just different signals may represent same type of quantity, in this case temperature, but the way we map them to bits may be entirely different. So just something to kind of bear in mind. So now what happened, if you think about this function, so this function is this combinational logic. It is taking 2 temperatures, the current temperature and the preset temperature, and then it has to output this 1-bit signal, which is going to control the fan, and that 1-bit signal indicates whether temperature A is greater than temperature B or not. So if we kind of just walk through this thing, I mean, we are really looking for A greater than B. So first row, I had 50 and 60. So answer is no, because we are looking for A greater than B, and 50 is not greater than B, so N. And I can kind of walk through this thing. Next value is also N. So 50. Next value is also N, and so on and so forth. So I can kind of walk throughout here. But then when I hit the lower rows, then we start hitting the regime where the current temperature is greater than the preset temperature. So 70 is greater than 60, 70 is greater than 65, 70 is greater than 7 is equal to 70. So it will kind of depend how we kind of treat it. So yes, yes, no, no, and then again 80 is greater than all the values. Yes, 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 yes. So nothing deep happening out here. It's just representing the fact that our relationship A greater than B is false or no for some value rows, and yes or true for some other values. So this is just a factual sort of representation of what we want our system to do. When should the fan turn on? Well, fan should turn on whenever the output A greater than B is true. So whenever A greater than B indicates yes. Now what we can do is we can take this and map it to our binary signals. So I can create another table where now this time around, instead of thinking in terms of 50 degree, 60 degree, and so on and so forth, I'm going to map things into to binary logic. So recall 50 was 0, 0, and 60 was also 0, 0, but for this signal. So I have a row saying 0, 0, 0, 0, and then A greater than B, well, is no. And like I said, very commonly, no or false is represented using 0. So I have an output of 0 out here. So what I want my digital logic to do is, if it sees input 0, 0 on A and also input 0, 0 on B, so this input is going to look like 2 pieces of wire coming in for A, another 2 pieces of wire coming in for B, and then I have a single wire coming out for the output, and the voltages on this may indicate 0 or 1. So we talked about it last time, that how we can map voltages to logic values. So 0, 0, 0, 0, and I want at the output a voltage which will correspond to 0. So that's what the electrical system would do. If I was designing the same system using, let's say, a mechanical technology, then 0 and 1 may correspond to position of some gear or something like that. If it was a chemical computer, then it might be concentrations or could be anything. But very commonly we design things electrically, so 0 would correspond to some voltage for 0. What about the next row? What do you think the next row would look like? So what will go in column A? Still 0, 0. Column B, 65. So we'll pick it up from here. So it would be 0, 1, and the output would be 0. So that's what we end up with, 0, 0, 0, 1, 0, and we can kind of walk through this thing. So special interest, like let's say we go to row 70, 60. Well, 70 is 1, 0, 60 is 0, 0. So we get 1, 0, 0, 0, and the fan is on. We have a yes out here, and the output would be 1. So in this particular case, the fan is on for 6 possible situations, the 4 bottom rows and 2 of the other rows that we are seeing. So the structure where we kind of explicitly list what values the inputs are taking, and what value the output is taking is something which is called as the truth table. Okay, so this we'll see that later also, but this is what is called as the truth table. So this is just an exhaustive listing of every possible scenario. And needless to say, since I have input A has 2 bits, it can take 4 possible values. Input B has 2 bits, it can take 4 possible values. So total combinations are 4 times 4, 16. So I have 16 possible rows. And then I have an output of a single bit. So I have a single column. Now, more generally, my output can have multiple number of bits. My inputs may not have the same number of bits. So like in this case, it so happened that A and B both had 2 bits each. I could have a system where, let's say, one input has 1 bit, another input has 3 bits, or any other arbitrary combination. And also, I may have multiple distinct outputs. So in this case, I just had a fan on, but maybe, let's say, I also have, I don't know, a warning light, so some sort of a temperature too high type of error message coming out or something like that. So I can have a system which may have multiple outputs as well. Okay, so that's a truth table. Okay, so let's imagine another situation where I still have the 4 current temperature, but let's say I have a preset temperature with only 3 possible preset temperatures, 60, 65, and 70. And let's say I decided to map them as 60 being 0, 0, 65 being 0, 1, 70 being 1, 0, so there's no 80, which was 1, 1 previously. So in this particular, sorry, no 75, I guess that's what I had previously, right? Yeah, no 75. So so I don't have any rows corresponding to preset of 75. In this case, my truth table does not have, no longer has 16 entries. It only has 4 here, 3 here, so total of 12 entries. So it's a truncated truth table. So some missing rows out here. And what do you think should happen? So if you look at B, there is nothing corresponding to 1, 1 out here. Okay, so what do you think would you do as a system designer faced with something like this, right? I mean, so I'm designing a system. I have 2 2-bit inputs. I still need 2 bits out here because I have 3 possibilities. But the second input B, I have not defined for you what happens when 1, 1 appears. Okay, so what are the different ways you could approach designing a system like this?
Declare an error.
Okay, declare an error is 1. So it's out of regime. So a possibility could be that there's some sort of a error LED and maybe I'll light it up, or maybe some sort of a display or something like that. So that's one possibility. What other approaches you can take?
You could like prefer to have the system safe, so you could say like if there's an error, then we just assume there's an error and we'll turn the fan on just in case.
turn the fan on or off, or whatever the safe state. So I could have a clear notion of a safe state and then go for that. Now, in case of fan on off, it's not clear which is safer or not. But like, let's say, for example, I don't know, if it was controlling a robot arm, maybe you'll stop the robot arm instead of moving it, okay? Or it's a car, maybe you'll just make it maintain its current state, not kind of change things. So you could have some sort of a notion of a safe state and go to a safe state. And a third possibility is that you can say, I'm going to assume that this will never really happen, okay? And if it happens, then all bets are off, okay? So you kind of just make the user sign a liability waiver form and kind of go with that. So that's the third possibility. And so in any case, mapping it to bits, kind of we end up with the right table, and that's what it looks like. So just a special case. So question I basically entered that the part of my input space I had left undefined. And in digital logic design, we often refer to as don't cares. That is, there are certain input values for which output is not defined, and we would basically therefore say that any output is acceptable. So fan could be on, fan could be off, I don't care. I would make use of that flexibility to design a cheaper system. So, but alternatives which were suggested that maybe I should have an error message, maybe I should go into a safe state, those are all possibilities, but then I have to explicitly kind of list those things. So these are called don't cares. It's unlisted rows on the table. Okay, so very commonly the don't cares are listed as an X or a D or a dash or some other special symbol like that. Here we are using D for don't care. So which basically means that when I'm designing this system, as a designer, I have the flexibility to interpret any row where a D is appearing as either a 0 or a 1 on the output. We don't care which one. And usually the guiding principle would be, so I could pick, I would say it's a 0 here, and I would say maybe it's a 1 here, and 1 here, and 0 here. I could pick whatever is convenient, and usually the guiding principle would be whatever may result in a lower cost system, smaller system, cheaper system, lower power system, faster system, whatever. Maybe some metric that you may have which may guide your choice out there. Okay, so so I basically have a truth table with a don't care. So combinational logic is memoryless. Okay, so this was what we discussed, was an example of that. And a more general combinational logic looks something like the following. It has a bunch of inputs and it has a bunch of outputs. Okay, in our previous example, I had 4 input bits and I had 1 output bit. This is an example where I have n input bits and I have m output bits. And using our compact notation, I may again write them as I have a single input I, which has n bits, and I have an output O, which has m bits in it. And mathematically, this combinational logic corresponds to some function f, which takes I, this n-bit input, and produces O in the m-bit output. And it has a property that if I change I, then O changes immediately or almost immediately. Okay, I mean, real circuits will have some delay, but the idea is that if I change I, O changes, and O depends only on the current value of I and not on some previous history at all. So there is no memory in the system. So literally, it is a pure mathematical function. And it could be an arbitrary mathematical function. And in fact, you could imagine that one way of implementing this combinational logic could be some sort of a table where I give the logic I, it looks up in the table in the ith row, fetches the output from it, and puts it on the output. Okay, so it could be designed in that way, but there are many different ways of kind of designing that. And as you can also see, this is a very general way of thinking about a function. If you go back to your math classes, a function is defined as a mapping from a set of values to another set of values with the property that for any given input, there is a unique output. That's literally what we are doing. I'm taking for every possible value from the input space. I'm defining, I'm mapping it to a value in the output space. Of course, the same input value may map, two different input values may map to the same output values. That's possible. So the function doesn't have to be one-to-one or on-to, but it is a function. Let's take different examples. So let's say I want to make a digital calendar, kind of things that you might find, let's say, in your nightstand clocks and things like that. So somewhere deep inside them, there might be such a circuit. So what this seeks to do is the following. It takes today and it produces a digital representation of tomorrow. So sometime at midnight, it has to change the representation on the display of what the date is. And in our case, what we're doing is we are representing the date as a month, day of the month, and day of the week. So 4 bits for day of month, 5 bits for 4 bits for the month, 5 bits for the day within the month, and 3 bits for the day of the week. And then I have to calculate this logic, given this computes, gives me tomorrow's thing. So how would this thing work? What would be kind of the strategy that you would use for computing tomorrow?
Well, for day of week, you could implement like an adder and have a modulo operation.
Good. So I do +1 modulo 7. Okay. Month. What would you do for month? Anyone? What would be? Let's say you're writing a program. What would you do for month?
Like +1 is like the day of month is over 30.
That will fail for certain months, but kind of the idea is if I look at the current month, if it is a month which has 20, if it's February, you have a special case. If it's month 30 days, you have another special case. If it's a month with 31 days, you have another special case. You look whether you are on the last day and then add one, right? So that's how you would do. So it's kind of a messy, it's an addition with a bunch of special cases attached to it. And then day of month kind of depends also on that. Okay, I mean, I'm going to add, but then I may have to go back to 1 depending upon what happened. Okay. So at least if you were writing a piece of software, it would be kind of easy. We don't know how to kind of do it in terms of gates, but not all that different conceptually. Now, what this notional clock, nightstand clock might do is the following, that at midnight, I get some sort of a special signal, and we'll see later in the course how it might work. And what I'm doing is the following, that in this, I have this special circuit which at the stroke of midnight is going to read its input and display it on the output, put it on the output. But otherwise, it doesn't do anything. Okay, so this is not a combinational logic. This is not of a form where if I change the input, output changes immediately. What it is doing is at the stroke of midnight, it copies the input to the output, or it copies the input into something internal, and that internal is what is being shown on the output. Okay. Whereas this circuit, compute tomorrow, is a combinational logic, and what it is doing is whatever is the input, it always shows to me the next day on the output. So if I change the input, the output will change almost immediately, barring some natural delays in my physical circuit. So what's happening out here is I'm taking the output of the special circuit, feeding it into this compute tomorrow, and taking the output of this compute tomorrow, and I'm feeding it to the input of the special circuit. And the special circuit, like I said, is going to update its output only when midnight, something special happens at midnight. A tick comes, and let's say that tick is a pulse on this midnight line. Okay. So some sort of a quick pulse comes, and it copies the input to the output. And otherwise, it doesn't do anything. So what will happen in a circuit like following? Sometime during the course of the day, I have the correct value on the day, and this compute tomorrow would have calculated the value of tomorrow. But this value will just sit out here. This special circuit is inactive because it's not midnight. At midnight, a pulse comes out here, and then the value of tomorrow now gets copied out here on the output, and therefore the clock phase will change. And this pulse goes away, so this at the clock tick a copy happens, and then after that, sort of we are back to square one, and then the new value which appeared on the output of this special circuit is now going to go through compute tomorrow, and I will have a value of tomorrow, and it will sit there. It will sit there for almost 24 hours until the next midnight, where again this copying will happen. So if you think about this guy, this thing is not behaving like our combinational logic at all. It is active only whenever this midnight happens, and otherwise it is not. The output is not following the input. So one way of thinking about it, it has memory. It is basically trying to. The output is what the input was at the most recent midnight. Right? That's one way of thinking about this box. That output is equal to the input at the latest midnight point. And that's a form of memory, right? I mean, we are remembering what happened at the most recent midnight. So it's an unusual kind of box now. It has memory. It has memory of what was the input at the most recent midnight. So we'll see later in the course how to design these kind of circuits and what this notion of a midnight tick might be and all. So we'll kind of see that later on. But again, the point I want to emphasize is that this box has memory, whereas this box, the compute tomorrow, is just a mathematical function. It's always outputting the next day, and if I change the input, then immediately, and again, immediately in any physical circuit would mean some tiny delay. Usually, electrical circuits can operate. What kind of how fast do you think electrical circuits are? What kind of delays do you think we see? Huh? Yeah, or even faster. What kind of clock speeds do you hear about now when you buy a PC or a few gigahertz, right? So they are less than a nanosecond. So they are hundreds of picosecond nowadays. Okay, and there are faster stuff also. So you're in the right ballpark. I mean, of course, things have come long ways. If you go back to early days of electrical circuits and all, things were in kilohertz or even slower. Okay, so we have come several order of magnitude improvement in recent decades, the so-called Moore's law and all that you often hear about. So there's always a tiny delay, a little bit delay before the output will kind of appear, and likewise there's going to be some tiny delay. Midnight tick comes, output will copy the input after a tiny delay, and it's going to be picoseconds, usually with modern technologies. Okay, so that's a weird circuit. It has memory, and we are looking at signals which have this notion of an event. Something happens at a specific point in time. Just at midnight, something special is happening. So event type inputs which are happening. And needless to say, my whole circuit also has memory, right? I mean, because this thing has memory and this thing doesn't. So I'm combining a box without memory with a box with memory. And generally speaking, when I connect these two kind of things together, I'm going to get a system which will also have memory. Clearly, this clock shows to me today what it is, and of course, the display depends upon what happened at the most recent midnight. So the overall system also has memory. That special circuit, we'll see later in the course, is something called register, and that special signal, midnight tick, is something called the clock. The example is just coincidental that midnight relates to clock and all. I mean, clock is a general term used in these things because clock is how a clock is a special signal in digital systems which periodically goes up and down. Okay, so when you hear like a PC has a 5 gigahertz clock, well, that means I have a signal which is going up and down at a frequency of 5 gigahertz. So every 200 picosecond, the signal flips. Okay, changes state from 0 to 1. So this register has the special property, kind of very similar to what that box had, which is every time a clock tick happens, so every time the clock signal, let's say, goes from 0 to 1, it is going to copy the input into the register. So think of register as kind of a holding area, a circuit which just remembers something. It's a memory. And output always shows whatever is in that memory. So the memory is updated only at the clock tick, but output always shows whatever is in the memory. Okay, that's how registers work. If you have played with Logisim, the tutorial was just about combinational logic. But if you see in the palette on the left hand side, you would see a box called register. And if you pop it into your canvas, you would see that it has a clock signal. And in Logisim, there is also a clock generator. The clock generator, if you monitor it, output changes between 0 and 1. So Logisim obviously kind of supports these kind of boxes. So we have this register. Register has this memory. Memory gets the value on the input whenever the clock ticks, and very commonly we put, so in this example we say clock ticks whenever it goes from low to high voltage. Okay, so the special symbol that you are seeing, okay, this is basically saying that it's a that the clock tick happens whenever the clock signals are going from low to high. I may also have a clock in the other direction, and that would be a clock drawn like this, and that would mean that the clock tick happens when the signal goes from high to low. Usually one direction is when the clock ticks. It's almost never the case that you will see the circuits where the tick happens on both high going and low going signals. Okay, it's either voltage low to high or voltage high to low, or logic 0 to 1 and logic 1 to 0. Output is always equal to whatever is in that memory. Okay, so memory is updated, input is copied into the memory whenever the clock tick happens, and output is equal to memory all the time. So that's our digital calendar. Now, one thing that we are also seeing out here is, and you already in the tutorial saw, that we can make more complicated things by wiring up simpler stuff. Okay, and in this case, we wired up a register with this combinational logic. So I've silently replaced that special cyan colored box with this register. That's what it indeed is. And in the Logisim tutorial, you saw that a bunch of different kind of gates were used to build a more complicated example, and in the discussion sections you will see some more of those. So this notion of composing complex circuits from simpler ones is how we make complicated digital systems. And in fact, one way of thinking about this whole course is we are starting with the simplest primitives, kind of very basic gates, and gradually we will learn how to make more and more and more complicated things. And by the time kind of you end up making entire computers and all, I mean, everything is just combine simpler things to make more complicated things, combine them into more complicated, and so on and so forth. Not much unlike, let's say, in programming, when you write functions and or procedures or methods, and you combine them to create even more complicated things. So you write objects, and you kind of create more complicated objects by combining them. Same kind of thing which is happening out there. So, for example, that thermostat thing that I had earlier on, I could do something like the following out here. So I can take my thermostat example, and its output. So this is, recall, this one was basically saying, is the temperature too high? Is the current temperature higher than the preset? So I have this box which is telling me that the temperature is too high. That is, current temperature, which is measured by some sensor, is higher than whatever the preset value that the user has given. I may have another circuit which is giving me the today's date, which is what we had in the previous slide. So I have today's day of week. So I'm just looking at that signal. Then I have a box which says whether this day of the week has a specific value, in particular whether it's a Sunday. So I combine these two. So output of this is basically saying whether today is a Sunday. And then this symbol that you are seeing is what is called as a logic NOT. What it is doing is it takes logic 0 and makes it 1, or takes a 1, makes it 0. So it inverts the sense of the logic. So if today was a Sunday, then the output of this NOT gate would basically say today is going to be valid. It's going to be high logic 1 or true when today is not a Sunday, right? So this one is basically this is basically saying true if today is Sunday, and this guy is saying true if today is not Sunday. So what do you think now? And then this gate is an AND gate. What it does is it basically says output is true or high if both the inputs are high or true. So both of them are true. So what do you think this overall system is doing? Any volunteers?
If the temperature is high on a day other than Sunday, then the fan will be on.
Okay, so if temperature is high and today is not a Sunday, then the fan will turn on. So we are basically, if it's a weekend, we are not letting it. So so this is high only if let me see, today is not Sunday. So the fan is enabled only if today is not Sunday. So that's kind of the idea. So the NOT gate complements its input. 0 becomes 1, 1 becomes 0. Another name for NOT is inverter. So it's also called inverter. It inverts the logic, or simply, and NOT gate is kind of the other term. AND gate outputs 1 if and only if both the inputs are logic 1, and if 1 is used to represent true value, then it's basically saying output is true if both the inputs are true, which is how we think of this in mathematical terms. In mathematics, AND is also called conjunction. But AND is the very common, is a more commonly used thing. This is more to the point. This is an AND gate which has 2 inputs. I can have AND gates with k inputs, which then the output would be true if each one of the k input is true. So I can have a k input AND gate, whereas a NOT gate is always only with a single input. Okay, so it's Sunday, it's not Sunday, we kind of see this thing. So fan is turned on when temperature is high, except on Sundays. Okay, so common type of gates. NOT gate, we already saw. AND gate, we already saw. On the right-hand side, we have what is called as an OR gate. And an OR gate is high. Output of an OR gate is high if any of its input is high. So it's basically saying either input 1 or input 2 or input 3 or input k, if any one of them is high or any one of them is true, then the output is high. This one in the middle bottom row, it's like the AND gate, except that I have this bubble at the output. And you see this bubble also occurs in the NOT gate. So this is really a merger of the two. It takes the AND gate and puts an inverter at its output. So the name which is given to this thing is called NAND gate. And it has the opposite sense of AND. It's basically saying output is false or 0 if and only if all the inputs are 1 or true. So that's the NAND gate. So it's an AND gate followed by an inverter. And likewise, on the bottom right, we have the NOR gate, which is nothing but the OR gate followed by an inverter, which is basically saying its output is 1 if and only if all its inputs are 0. So those are straightforward mapping, but the one at the very bottom left is the so-called XOR gate. And that's what the tutorial is doing. And it's, if you see, it is drawn like an OR gate, but with an extra line out here. And an XOR gate outputs a 1 if and only if an odd number of inputs are 1. So in particular, if I have 2 inputs, then it's basically saying output is high if exactly 1 input is high, and the other, so the other must be 0. So if I look at an OR gate will output high if inputs are 0, 1, or 1, 0, or 1, 1. And it will output 0 if input is 0, 0. Whereas an XOR gate is going to output a high when inputs are 0, 1, or 1, 0, but it's going to output a low if input is 0, 0, or 1, 1. When generalized to more than 2 inputs, it basically says odd number of inputs are 1. So if I had, let's say, a 3-input XOR gate, then if 1 input or all 3 input are high, then the output will be high. In programming languages, how do you use XOR? Anyone recalls from any language? Like, what symbol do we use for XOR doing an XOR operation? That's okay. So caret is used in some languages, and in mathematics we use circle with a plus sign inside it. So these are sort of common ways kind of representing. There is also something called XNOR, and as you might imagine, XNOR is nothing but an XOR with a inversion at the output, so a bubble at the output. So generally speaking, anytime you see a bubble, that means there is a NOT gate. So for example, I could draw something like the following. Let's say I draw this. What this is saying is I have an AND gate whose top input has an inverter in front of it. Okay, so bubble means inversion. Okay, if I have 2 bubbles in succession, you can cancel them out because inversion followed by inversion is an identity operation. So these are common type of gates. Clearly, looking at this, I can make a NAND gate using inverter and AND gate. I can make a NOR gate using an inverter and an OR gate. Later on, we will see that I can likewise I can make an AND gate by using an inverter and a NAND gate. I can make an OR gate by using an inverter and a NOR gate. So as you can see, I have redundancy in these things. Not all of these gates are essential. Later on, we can see that how we can go back and forth between these. So like using NAND gates, I can make I can make OR out of AND out of OR, so I can go kind of back and forth between these. Looking at this, can I make an inverter out of NAND gates? Anyone? So how would you do it? So let's say I give you infinite supply of NAND gates. Can you make an inverter? I see you saying yes. Anyone else believe you can? And yeah, go ahead. Yeah, so I want to make an inverter out of an infinite supply of this.
Yeah.
So how would you do it? Yeah, go ahead.
Can you just tie the 2 inputs together?
Excellent. So I tie the 2 input together, and then I have an inverter. And you can convince yourself because NAND gate outputs a 0 if both inputs are 1. If I tie them together, then if the input is high, output is 0. If input is 0, output is high. So the suggestion out here is that I tie them together, and then what I have is equivalent to 1. Okay, so that's basically what's happening. So I can do that. What about from a NOR gate? Same story. I can tie the input together, get an inversion again. Okay, so inverter is redundant. AND gate is redundant. OR gate is redundant because I can get them using this. Later on, we'll see that I need only one of these. So in fact, there is a concept of something called universal gates. A universal gate is a gate using which I can create every other possible gate. And it turns out NAND gate is universal, NOR gate is universal. Okay, that is any imaginable logic function I can implement just using NAND gate, in fact just using 2 input NAND gates, And likewise, any imaginable logic function I can implement just using 2-input NOR gate. Okay, so this is universal, this is universal. Inverter plus AND is also universal because inverter plus AND is equal to NAND and therefore is universal, and so on and so forth. It turns out XOR is not universal. XNOR is also not universal. So if I just give you an infinite supply of XOR gates, I cannot implement things. In the tutorial, you are seeing that I can implement XOR gate using these other gates, but you cannot go the other way around. In general, you cannot go the other way around. Okay, closure property. So closure in mathematics means that I give you some variables, I apply an operator to it, I get an output, and it belongs to the same set. So a set is closed if I take 2 elements of that set, I apply some function to it, let's say addition, and I get back a new value which is again in the same set. So that set is called closed under the operation that we are considering. Combinational logics are closed under what is called as acyclic composition. So what that means is, in plain English, let's say I give you combinational logic boxes and I let you wire them up. When you wire them up, as long as you do not create cycles, that is, I have never a situation where an output goes back to an input and so that I can trace through this graph and come back to wherever I started. So I don't have a cyclic graph. So as long as I'm wiring them up without creating loops, then the new circuit that I will have, the new logic system that I'll have, will also be combinational. Okay. In fact, if you recall the earlier slide where I had that memory related box, it had a loop in it, right? I mean, we were taking the output of a register, feeding it through the tomorrow's logic, and bringing it back to the input of the register. So it had a loop. So loops are essential for memory. So without loops, you cannot have memory. So if I do not create loops, and so if individual boxes were combinational, then the new circuit will also be combinational. Namely, it will be memoryless. So loops are essential for having memory, but I may have circuits with loops which may not have memory still. Okay, so loops do not guarantee memory, but loops are required for memory. Or another way of saying is loops are necessary for memory, exhibiting memory, but they are not sufficient. So is this combinational? No loop, so combinational. Is this combinational? Well, it has loops in it. I can kind of trace through kind of this. So there are loops in it. Is it combinational based upon what I said? It may still be combinational, but it's possible also it has memory. It depends upon. So the thing is, generally speaking, when you have loops, it will not be combinational. But again, there are special cases where it could still be. Okay, so loops do not guarantee, but so special cases can still lead to this. Yeah.
When would it be combinational?
Okay, to give you a trivial example, let's say this logic always output false. So it's independent of this input. So these are degenerate cases that you will see. But there are also other trickier cases where kind of the effect cancels out, which could be like, for example, whenever the pathway from this input to output on the upper box is active, the lower box doesn't have an effect. Okay, so there are special cases that you can create. But generally, so the stronger statement obviously is if there is no loop, it's guaranteed combinational. But if there is loop, you have to check carefully. So circuits with memory, that is those whose output depends upon history of the inputs, are called sequential logic circuits. So sequential logic circuits are basically anything with memory. And therefore, when we talk about in computers have memory of different forms, like you have DRAMs, those DIMMs that you buy and plug into your computer, disk storage, these are all examples of memory. So they are examples of sequential logic systems. So, so a sequential system could be just plain memory, but it could also be behaviors which exhibit memory. And we talked about it in the in Monday's lecture, like things like a system which is counting how many cars are in the parking lot. So every time a car enters, it increments. Every time a car leaves, it decrements. And that's an example where it has memory in the system, even though it's not just doing a memory function, it's also doing some computation. So key thing is output is a function of history as well as current inputs. If a system with memory makes use of a clock signal, which I talked about earlier, then it has given a special name called synchronous. So synchronous means that not only it has memory, but it is also making use of a clock signal. So what it means generally means is that things change in such a circuit only when the clock ticks. Otherwise, the system is stable. So almost every memory full system currently in practice that you would see, electronic system, are designed with a clock in it because it keeps design life simple. We'll see that later in the course. But clock is not essential to having memory. Okay, so you could have systems, and there are a lot of examples. Our brain is a sequential system, but it doesn't have a clock. So there are plenty of examples of systems in nature and artificial systems which are sequential, but they do not have memory. So they are not synchronous. In particular, they're called as asynchronous sequential systems. In what we saw today, register, just its behavior is sequential, and the overall system is also sequential. And we saw plenty of examples of combinational, like the comparator, the tomorrow's circuit, and so on and so forth. They're all examples of plain combinational circuits. So again, to kind of re-emphasize then, summarize this module, so two types of digital systems: combinational, no memory, output depends on the current input; sequential, has memory, output depends upon not just current input, but also the inputs which came previously. And then the sequential circuits have two broad categories: those that need a clock to run, in which case they are called synchronous, and those which do not need a clock to run, and they are called asynchronous. In normal design, current computer design practice, asynchronous sequential circuits are rather rare. Most design is done using synchronous because they're easier to design. But there's no particular fundamental reason that it has to be that way, basically. So, any questions on this? Okay, so let's move to next module. So what we are now going to look at is how to so the way the course is organized is we go, as you can imagine, simpler systems first. So we start with combinational systems first, and we're going to look at how we can design these things in a more systematic fashion. And the mathematical machinery underlying this is what is called as Boolean algebra. And you've sort of seen this stuff possibly informally in sort of your math classes and all, but we are sort of going to go through it, and many of you probably haven't, and certainly there are things that you haven't seen. Okay, so what's Boolean algebra? Well, what's algebra? So we all study algebra. In algebra, we are given some variables, we apply some operations over them, and we are given some properties about this. And normally, I mean, you sort of grow up studying, and operations that we study are things, the arithmetic plus and the arithmetic multiplication and things like that. Boolean algebra is an algebra in a similar sense. That is, I have constants and variables and operations, except the key thing out here is that the values that those constants and variables can take are binary. That is, they can take two values, and very commonly we call them 0 and 1, or maybe false and true. And we have three operators. We have the AND operator, which is written as that caret symbol. That's not so upside down V. The OR symbol, which is the V symbol, and the NOT symbol, which is this funky little symbol. Okay, so AND, OR, and NOT, these are kind of the three basic primitives that we have. And AND operation means, so if I have two Boolean variables A and B, then it says A and B is 1 if and only if A and B are both 1. Okay, so that's the intuitive notion of AND. OR operation says A or B is 1 if A is 1 or B is 1. So as you can see, 1 means true intuitively and 0 means false. NOT operation, not A is 1 if and only if A is 0. Okay, so that's how NOT is defined. These things A and B, kind of the variables, like the X, Y, Z in normal algebra, they are called literals. So A, B, these are called literal symbols. They're kind of like the signals, the variables in our design. If I think in terms of truth tables, then this table at the top is showing the truth table for A and B as well as for A or B. So first two columns are A and B, and since I have two variables, I have four possible values: 0, 0, 0, 1, 1, 0, 1, 1. A and B, this purple color one, it takes the value 0 for the first three rows and is high only if both A and B are 1. A or B is high if for the final three rows, so if any one of the input is 1. So this straightforward mapping of the definition. NOT function is written like this, and if A is 0, output is 1, and vice versa. If A is 1, output will be 0. Other symbols which are used for NOT include this tilde sign, this apostrophe, as well as a bar drawn on top of A. So this is just definition. Just one sort of note and on notation and what would be acceptable and not acceptable in terms of when you submit assignments and stuff like that. For OR logic, this V symbol or a vertical bar is okay. I will not accept plus. Okay, and the reason is plus carries the connotation of mathematical addition, and some properties of OR are different. So even though in some systems and languages, plus is used for logic OR also, but I'll not accept that. If I have a series of OR, then you can use sigma. Okay, and okay, so there's a slight semantic inconsistency. I'm not allowing you to use plus, but I'm allowing you to use sigma, but that's how kind of it's done in Boolean algebra. So sigma AI, where A sub I stands for A1 or A2 or all the way to AN. For AND, you can use the upside down V, or you can use the ampersand, but you cannot use the multiplication sign, you cannot use the dot sign, you cannot just say AB to imply A and B. So all those are unacceptable. If you want to indicate a whole bunch of ANDs being done, you can use this pi symbol, product symbol. So that's just kind of a side note. So several ways to describe a combinational logic function. Okay, so let's look at an example. Let's say I'm looking at what is called as a majority circuit. We'll encounter it again and again in the class. So let's say I have a system which takes three 1-bit symbols, three Boolean signals A, B, and C. And I want the output to be 1 if majority of the inputs are 1. So you can think of it like maybe it's some sort of a voting system. A, B, and C represent 3 votes. Positive, someone voting for voting yes means the corresponding signal is high. And I want the output to indicate whether the measure won or not. So for example, 0, 0, 0 means everyone voted no. output is 0. On the other hand, let's say 110 means 2 people voted yes, 1 voted no, so majority voted yes, so output is 1, and so on and so forth. So, so in this particular case, 011, 101, 1100, and 111, these are the 4 cases where I have the output high. If I look in terms of logic equation, I could express it by saying output is equal to A and B, or A and C, or B and C. So A and B means A and B voted yes, A is high, B is high. A and C means A and C are high, so I don't care about B. And then B and C means B and C. And any one of these cases being true, I want to vote high. So if you think about it, A and B corresponds to row number 7. A and C corresponds to row number 6. B and C corresponds to the row number 4. Why do you think I don't have a A and B and C?
Any one of the two
Will collectively imply that, right? So if I could have written or A and B and C, but that would be redundant, okay? Because if A and B and C is true, then all the other 3 rows are going to be true. So they are redundant. So same concept, same combinational logic, I'm able to express, one can write it as an English description, as a truth table, as a logic equation, and of course our aim is we want to eventually get to a circuit, gate level implementation. And kind of in a way, as a designer, your task is to take this English language description and then gradually, through assistance of truth table and logic equations, come to the gate level implementation of the system. So Boolean algebra provides us a way to kind of mathematically treat all of this. So just like any algebra, the one which you have studied in your mathematical courses, there is a set of rules underlying this thing, a set of properties, and they are the axioms of Boolean algebra. So a set of mathematical statements which we assert to be true. So, and there is no proof for this, okay? I mean, these are just assumed to be true. And so one is that there is an identity. 0 and any Boolean variable is 0. So it's basically saying if I'm ANDing something and one of the input is 0, the output is 0. 1 or x is high. So it's basically saying that if I have an OR gate, if you think in terms of gates, if I have an OR gate, one of the input is high, then the output is high. Of course, Boolean algebra was done before gates were existed and all, so this is just pure math. So it's basically saying 1 or x is 1. 0 and x is 0. This is properties. Idempotence is basically saying 1 and x is x. And if you think about it, it makes sense. 1 and 1 will be 1, and 1 and 0 will be 0. So therefore, 1 and x would be x. 0 or x is x. And that also stands to reason because 0 or 1 is equal to 1. And 0 or 0 is 0. So again, therefore, it holds true for an arbitrary x. So identity, idempotence, negation. Not of 0 is 1, not of 1 is 0. So this properties of 0 and 1 now. And then just from these 3 axioms, I can define, one can derive a whole bunch of other properties. Commutativity, you have all seen it in arithmetic and algebra. X and y is y and x. X or y is y or x. So you've seen it many equivalent in arithmetic. Associativity, x and y and z, I can kind of put the parenthesis elsewhere, okay, and I can do the same thing with OR gates. So if you think in terms of gates, what this means is that, let's say I had a circuit like this. Then I could also write it as the two do the same thing. Okay, so just a gate view of the things out here. So that's associativity. Yeah.
Does associativity for this require all of them to be the same sign?
To be the same?
Not to say are they all have to be the same function? So they're all like and or all ors or
Okay, so associativity is defined only in terms of the same operator. Okay. So just like in regular algebra, associativity for plus and then associativity for multiplication, you can kind of define that. Okay. What you are thinking about is distributivity, where you mix two operators, and we will see that shortly. So distributivity. So what this says is x and y or z is the same as x and y or x and z. That's the counterpart of distributing a times b plus c is the same as a times b plus a times c. Okay, and this is where we differ from regular arithmetic or algebra. We distribute multiplication over addition, but not addition over multiplication. You cannot say a plus b times c is the same as a plus b times a plus c. That's not true. But here, distributivity works both ways. I can also say x or y and z is the same as x or y and x or z. Okay. So the point I'm trying to make is that here, as you can see, distributivity is working for both ways. But in regular algebra, I can certainly say x and y plus z is equal to x and y plus x times z. But I cannot say, so this is okay, but I cannot say x plus y times z is equal to x plus y times x plus z. That is not true, right? So, and it is precisely because of this I do not want you to be using the plus symbol and the multiplication symbol, because that analogy doesn't hold true, and therefore I would really like you to use kind of the proper symbols for these operators. So distributivity works both ways, and that kind of leads to some interesting properties out here. Idempotence, x and x is x, x or x is x. Absorption. Absorption says x and x or y is x. So let's kind of think about it. Okay, why is this true? Well, the y can take two possible values. Y can be 0 or y can be 1. Right? Let's take the case y is 0. X or 0 is the same as x, and then x and x is the same as x. Right? So that's true. So for y equal to 0, this is true. What about y equal to 1? X or 1 is what? 1, and then x and 1 is x, so this is true. So as you can see, one way of proving some of these things is to kind of think about these different cases. So the way I kind of convinced myself this was true was by saying that, look, what if y was 0? What if y was 1? Those are the only two possible cases, and the statement holds true for both of them. You can apply kind of the same rule for the other side also. So this is called absorption, and this is pretty powerful. And the reason kind of these rules are important is that you may have a complicated looking expression, and then you can simplify them by applying these things, much like we do in algebra. You kind of start with some complicated expression and then simplify them gradually. Combining, this is even more powerful. So it basically says x and y or x and not y is the same as x. So if you kind of speak it like just normal, if x is true and y is true, or if x is true and y is not true, then x is true. It kind of makes sense because I'm covering both the cases of y. Y does not matter, right? I mean, if y is true or y is not true, all I care about is x in this case, right? So x and y or x and not y is the same as x. So y can kind of cancel out, and it's the same way on the other side. X or y and x or not y is the same as x. And you can again check to prove it. Let's take the case y equal to 0. If y equal to 0, the first term x and 0, this would be 0. The second term, x and not 0, is the same as x and 1, which is the same as x. So I have 0 or x, which is x. So you can, so let me write it down for this one. So let's say case 1, y equal to 0. So in that case, this is x and 0 and x and not 0, which is the same as 0 or x and 1, which is the same as 0 or x, which is the same as x. And you can do the same thing for case 2. Case 2, y equal to 1, I'll let you kind of do it, and kind of same thing for the right hand side. So this is the combining property, which again is very useful in simplification. And next comes what is probably the most important property, and it actually has a special name for it, and it's called De Morgan's theorem or De Morgan's law or De Morgan's whatever. Okay, and what it says is the following: not of x and y is the same as not x or not y, and the sort of the dual of that is not of x or y is the same as not x and not y. So remember earlier on I said we can go between and or. It is this De Morgan which lets us do that. It's basically saying if I give you something in an and form, then I can go into something in an or form, or the same thing from the right hand side. I can kind of go back and forth between these. So this is the key to saying that I need only one type of gate. I need either the NAND gate or the NOR gate. I don't need both. And we'll see how sort of we use this property later in the course again. So this is called De Morgan's. Let's convince ourselves it is true. So let's look at the left-hand side version. Okay, so I'm going to focus on, I'm going to try to prove this. So one way of proving anything like this is just make the truth table. Okay, now there are times at which I may say you're not allowed to use a truth table. You must prove it using algebraic means only. But for purposes of the lecture, I mean, it's perfectly fine for me to list everything. So x and y, there are 4 possible cases. X, y both 0, 0, 1, 1, 0, 1, 1. And then I can list what the left-hand side value will be and what the right-hand side value would be. And you would see that the 2 columns are identical. And therefore, that statement must be true. And you can do the same thing for kind of this right-hand side version also. So De Morgan's law, basically, again, not of and is the same as or of the 2 inverted, and vice versa. De Morgan's law, turns out, is a special case of a more general property that is true in Boolean logic, and which we'll see very shortly. So let's look at how we can apply these Boolean properties we have seen thus far. So let's say I have this sort of complicated looking expression. F of A, B, C is A and C, A and B and C, not A, and so some randomly chosen function. And what we can do is we can kind of go through a bunch of properties, and I'll kind of let you think about it at home more. But main thing that we are doing is we first apply absorption property. So let's go back. Absorption said x and x or y is x, and x and y is x. Okay, so that's what absorption was. So what we are doing out here is that we are looking at this, and we are basically saying that A and C, A and B and C, so those are the first 2 terms, okay? And then I have this term which is not A and B and C. And what we can show you, what we can see is that that is the same as not A and B and C, or A and B and C. And likewise, the next term, A and B or and not C, I can OR it with A and B and C and without affecting anything. Okay, so this is coming directly from absorption. Again, let's stare at absorption for a moment again. So absorption is basically saying that if I am if I have something, then I can or it or and with or it or and it with something else, and it doesn't really kind of matter. Okay, so x is the same as x and x or something. So it's that property that we are kind of making use of out here to to, uh, to simplify things. Apply combining property, and then we apply sort of simplify things, and we end up with this function. And this function, if you recall, is our good old majority function. Okay, so we started with something complicated looking, and we ended up with the majority function. Walk through this example to convince yourself that kind of you're applying. It's kind of just plain algebraic kind of manipulation. And the reason sort of this is important is that a lot of computer programs and all work this way, which is you start with complicated looking expression, and then you apply these rules of algebra, and you end up with something very simple like this. Now, there are very costly computer programs which are sold by companies to, they're called electronic design automation companies. And their sole purpose is to take logic description and then simplify them so that I have cheaper implementation of logic gates. And then these companies sell this software to companies like Intel and all those who make the chips. And these software are extremely expensive. They go usually for like $100,000 per license per year, but then they're used to make chips which are sold in billions of dollars of revenue. So there's a lot of money at stake. And of course, they do not work just for these simple examples. They take examples with thousands of input variables and things like that. So very complicated things because they're designing chips with hundreds of millions of gates and all. Now, in later courses, if you kind of do some of those courses, you may get to use some of those tools. In this class, Logisim that you're using has very simple version of these capabilities built in. That is, there is a menu option in Logisim where you can enter equations, and it can simplify it and then create a simple gate. So that's one thing. Another one is, any of you heard of Mathematica or Wolfram Alpha? Anyone of you heard of Wolfram Alpha, right? Nice website. You kind of, Wolfram Alpha actually can take these logic equations and simplify them. So very powerful, useful tool. Just wanted to sort of mention that if you're doing homework and all, I mean, that's a nice little Boolean logic calculator to have, okay? And it lets you actually feed, I think the and or, it uses the ampersand and the vertical bar, okay? So you have to kind of switch things, but it can do the simplification. So it has a whole Boolean logic machinery kind of built in. In fact, it can even give logic gate descriptions, implementations also. So it's a pretty powerful tool. But again, kind of the specialized tools for chip design do obviously a lot more. Okay, let's see. Now, I mentioned that De Morgan's law is a special case of a more general property. So this general property is called duality, or dual of a Boolean logic function. So if I give you a logic expression, then its dual is obtained by replacing and by or, replacing or by and, replacing 0 by 1, and replacing 1 by 0. So let's say I gave you f of AB is A and B, or B and C. Then the dual of f, which we call as f with a superscript D, is A or B. So see how this and out here has been replaced by the or, and so this middle or has been replaced by the and, B or C. So B and C became B or C. So I can take any arbitrary Boolean logic equation and then obtain its dual. So this is just a definition. And of course, the dual function is a different function. I mean, this one, f of AB, and the dual of f are not the same function, but they still have a deep connection between them. And the deep connection that they have is the following. Let me jump a little bit ahead, okay? Dual of a function applied to complement of input variables equals to the complement of the function. Or stated more simply, if I have a function f then the complement of f is the same as the dual of f where the inputs have been complemented. Okay, so I had again inputs a, b, c, and I want to compute f of a, b, c. Then what I could do is I can compute the dual of f where I feed as input not a, not b, not c, and I can take the complement of the whole thing. So I can move this not on this side. So a function is the same as the complement of the dual applied on inputs which have been complemented. And if you see in this light, then De Morgan's laws, the two versions of the laws are actually just a special case of this, okay? Because the and was getting replaced by or, so that's the duality part, and then the negation was x and y were getting negated. So let's pop back about here. So let's look at an example of a dual. So let's say I give you this function. F of x, y, z is x and not y or not x and z. And let's say I want to calculate the dual of that. So anyone wants to help me out? So what would be the dual of this? Anyone want to help me?
Don't you just flip the times forward?
Yeah. So we flip. So we'll flip. So we flip and to or. So this and will become or. This will become and. This will become or. What else? Do I need to do anything else? No. So we don't do anything to not. Okay. So 0 becomes 1, 1 becomes 0, but not remain unchanged. Okay. So remember, if we kind of go back, the definition of dual was simply and by or by and, 0 by 1, 1 by 0. It said nothing about nots. Okay. So we are not doing anything to not. So in fact, they just carry over. So this remains x, this remains not y, this remains not x, and this remains z. Okay, so that's the dual. So given a function, going to dual is kind of relatively straightforward. So again, not is not changed at all. Okay. See this and, so let me just draw it. This is a switching. This is a switching.
We're supposed to convert to 1 and a 0.
But there's no 1 and 0 in this expression, right? So there's no 1 and 0 in this expression, so that part doesn't matter. It's very rare that you will encounter an expression which will have an explicit 0 or 1, but it's possible.
Right. So you would achieve that by putting knots on everything, right?
No. So again, so the let's say I'd given you this expression, x and 1. Okay, it's a stupid expression, but bear with me. Its dual would have been x or 0. Okay, so that would be the dual. Okay. Now, why? I mean, you could always make the case if I have ones and zeros in the expression, I could simplify them away. Okay, but that doesn't matter. That's not the issue. The main thing is if I'm doing the duality, then replace and by or by and, ones by zeros, zeros by 1. But it would be rare for you to find expression with explicit 0 and 1 in them.
So finding the duality is not the same as finding the De Morgan.
No. Finding the dual is just definition. I give you an expression and you find the dual. So thus far it has, so duality in itself has nothing to do with, it's just a definition. Okay. It turns out, like I said, that there is this property which we are not proving, which basically says that a function is the same as a negation of the dual of the function where the inputs are the negated inputs. And it is this guy which is the same as De Morgan. Okay, so let's see why it is the same as. Okay, so let's say my function f of xy was x and y not. So let's say this is my function. What is a dual of this function? So f of the dual of this function, can anyone help me out? What's the dual? Huh? not x or y, right? And then what this property says is that this guy is the same as the, so I can take f of ABC is the same as not of f dual applied on not x, not y, which I can write as, so this not and this not will cancel out, and I will have not x or not y. And that is De Morgan's law. So as you can see, De Morgan's law is just a special case of applying this equation on a specific function. So that's the connection basically that sort of we end up having. Is that clear to everyone? And kind of the other De Morgan's law can similarly be proven. So De Morgan's law, special case of duality property. Yeah. Sorry. Okay, so you should become very conversant with or comfortable with applying these properties to manipulate Boolean expressions. I mean, and in homework you are absolutely free to use Wolfram Alpha or any other tool like this. In exams, I'm going to ask simple version of these things. I'm not going to throw some complicated expression at you and expect you to simplify it. So. But for homework, things are fair game, and you can use these tools. Yeah.
Question on notation. For the complement or for the not, can we use the exclamation point?
You can the apostrophe you meant.
I meant the exclamation point.
For the not symbol. Yeah, you can use it. Okay. Yeah, my main concern is with the and or, because the plus symbol is very ambiguous, and you will miss out some of these properties otherwise. Okay. So again, to sort of what he's saying is, can I use the exclamation symbol? So can I, this guy is the same as not x, and that's kind of fine. I'll accept it. But to the extent possible, try to stick with the notation we're using, because the notation I'm using is the textbook is using that, and also is the more common notation, kind of more formal notation. Okay, so we already saw this. Okay, so next concept, min term. So it's again a definition. There is, but it's a very useful concept. So a min term of a function is an expression that ANDs together all the inputs of the function in direct or negated form. So it's a mouthful. So let's say I have a function which has three inputs a, b, and c. Then a min term of this function is any expression where a, b, and c are ANDed together, but one or more of them may be negated. So what I mean by that is a and b and c. That's a min term. Okay. Or not a and b and c is a min term. So all the three variable inputs a, b, and c are appearing. And then in this case, a, b, and c are all non-negated. In the second case, a is negated, b and c are not complemented. I have other examples, a and not b and not c, and so on and so forth. Okay, so how many min terms will f of ABC have? 8, right? Yeah, be confident. You're right. Okay, so you don't need to be quiet about it. That each input can appear negated or non-negated. So in general, if I have a k input function, I will have 2 to the power k possible min terms. So just a definition. So nothing deep about it. So, and if I have n inputs, it's 2 to the power n. Okay. Counterpart, as you can imagine, we had min term, so we have max term. Max term is where things are ORed together. So same story. I may have A or B or C, not A or B or C, A or not B or not C, and so on and so forth. And again, the same story. I'll have 8 possible. Okay, I kind of messed up here a little bit. This should say max term. Okay. So I have 8 possible max terms in this case. If I have a function with n input, I will have 2 to the power n possible max terms. Okay, so again, just definition and simple properties. Now, remember our truth table? So I can write down, if I have a function, so let's say I have a function of 4 inputs, D, A, B, C, D, and let's say I write the function inputs in this order, D, C, B, A. Then I can enumerate all possible values that the inputs can take. So it's 0, 0, 0, 0, 0, 0, 0, 1, all the way to 1, 1, 1, 1. I have 4 inputs, so I have 16 possible values. So I have 16 rows out here. And I can list them by looking at this binary number. So 0, 0, 0, 0 is binary 0, 0, 0, 0, 1 is 1, and so on and so forth. 1, 1, 1, 1 is the number 15. So, or they're just the row numbers, 0 through 15. Now, and what I'm stating next is a little bit of convention also, but I can map these inputs to corresponding minterms. So when inputs are 0, 0, 0, 0, that corresponds to the minterm. Remember, minterm is ANDing. That corresponds to the minterm where A, B, C, D are all complemented. So that's the minterm, not D and not C and not B and not A. But for the max term, it's the other way around. If there is a 0 here, that means it is not complemented. So the max term here is D or C or B or A. And this is convention, why we are doing it, but it turns out this convention has some useful properties, so that's why it's done that way. If you look at 0, 0, 0, 1, that corresponds to the minterm, not D, not C, not B, but since A is 1, so it would be AND A. So we'll see this term, not D, not C, not B, and A. What do you think will happen to the max term here? What would be the corresponding max term? So remember, for max term, the rule is if it's a 0, then it's non-complemented. If it is a 1, it is complemented, and otherwise you're using OR. So anyone, what would be the max term? So it would be what? Spell it out.
D or C or B
Or not A. Excellent. So it would be D or C or B or not A. And I can walk through all of these. Let's look at some another one, like let's say 1100, row number 12 is 1100. So therefore it's D and C are not complemented, B and A are complemented, they're all ANDed. That's the corresponding minterm. And when it comes to max term, D and C are complemented and A and B are not complemented. So it's not D or not C or B or A. Okay, so we can, given a truth table, I can write down for each row what the corresponding minterm is, what the corresponding max term is. Okay. By the way, one thing which is very important out here is the order in which you write things out here, and that is your choice. So I chose that the order was DCBA. If I had chosen the order to be the other way around, as in ABCD, for example, then spell it out this way, then the two truth tables would have different correspondence in the sense that 1101 in truth table, this truth table will correspond to some different row in the other truth table. So the order does matter. Now the reason we kind of list this out is we'll see that this makes actually life very easy to write spell out functions. And part of the reason it makes life easy is that instead of dealing with these complicated looking midterms, we are going to give them a compact name. So for minterms, we basically we represent them by a little m and then an index number. So we say minterm number 2 is the one which appears in row number 2. So in this example, where the inputs were written as DCBA, minterm number 2 is not D and not C and B and not A, and a compact representation for that is m of 2. And we have a similar compact notation for max term, which again is the same story, which is max term number 6 is the one which appears in row number 6, but we use a big M, uppercase M, to represent a max term. So max term number 6 is the one in 6th row, and therefore that is D or C, say D or not C or not B or A. So like, for example, min term number 13 would be D and C and not B and A, so kind of out here. And likewise, max term number 13 would be not D and or not C or B or not A. Okay, so again, just definitions thus far. Okay, of course, if I have a function with, let's say, 5 inputs, A, B, C, D, E, then I would have twice the number of rows, 32 rows, and therefore my min terms will go from M of 0 to M of 31, and max terms will go from M of 0, big M of 0 to big M of 31. So this is just compact notation. So anytime I write M of 2 and I spell out for you what order the inputs are and all, I can immediately go to what min term it is representing. Now, so that's all of that is definition. One other property you would see is something called dualization, and what it says is that the complement of a min term is the respective max term. Okay, so for example, if I have M of 5, which is this guy, with using De Morgan, I can write it like this. Okay, this is simply an application of De Morgan or duality, using the duality property, and which is the same as the complement of the min term. So I can go from max term to min term or vice versa by maintaining the same index number but complementing them. Okay, so now comes why. So why this min term? Why this max term? And the reason behind this is the following: that there is a concept of something called a normal form. So normal form in mathematics means a standard way, a canonical way of representing something. Okay, so and the reason it's useful is we saw that the same function could be written in many different ways. And so let's say I'm designing a logic system and you're designing the same one. I wrote the equation, you wrote the equation. How do we know they are actually for the same system? How can I say my equation is equivalent to your equation, your expression, your Boolean expression? So the way we can do it is we can say, let's both convert our expression into a standard form or a normal form, and then we can compare them. Because if it's a normal form, then once you convert to the normal form and I convert my expression to the normal form, they should be the same. And that's the concept out here. So it's something used quite often in science and math. So same concept out here. Now, it turns out there are two normal forms which are very of interest out here. One is called disjunctive normal form. And the idea is, in a disjunctive normal form, the function is represented by taking some min terms and ORing them together. It's often called as sum of products. Okay, sum referring to OR and product referring to AND. So another way of saying is OR of AND. Okay, but sum of products is a commonly used thing. So essentially what it is at the top level, I'm ORing things together. And disjunction in logic, in formal logic, disjunction means OR. So it's basically I'm taking a bunch of min terms and I'm ORing them together. That's why it's called disjunctive normal form. If my memory serves me right, I think our textbook actually has it the opposite, and they are wrong. Okay, so what I'm using in the lecture is actually the correct definition of disjunctive normal form and conjunctive normal form. So just be sort of careful on that one. Like I said, it's the first edition, and I think they kind of ended up messing things up a bit. So for example, f of a, b, c, written in this way, a and b and c, which is a midterm, ORed with a and not b and not c, which is another midterm because it has all the three inputs appearing, ORed with a and b, a and not b and c, which is another midterm. So I'm using three of the midterms, three of the 8 possible midterms, and I'm ORing them together. So a function can be represented as an ORing of some of the midterms, right? So let me throw a question at you. So let's say I give you 3 signals, A, B, and C. And I've just told you that a function is nothing but an ORing of sum of the minterms. How many different mathematical functions exist with 3 inputs? How many distinct Boolean logic functions exist with 3 inputs? Howard? So any thoughts? So remember, a function can be represented as ORing of sum of the minterms. How many minterms are there? 8. Okay. So in any given function, some of the minterms may occur, right? And the others may not. So a function is a way of selecting some of the minterms, because then I'm just going to OR them. So how many possibilities are there of functions now? So I have 8 minterms. Each minterm may occur or not occur. Correct? And I have 8 minterms. So 2 to the power 8. So I have 2 to the power 8 possible functions of 3 inputs. Okay, so 2 to the power 8 and it includes some trivial function, like it includes a function called fabc is equal to 0. It includes also the trivial function fabc is 1. So what is the function fabc equal to 0? It includes none of the minterms. Fabc equal to 1 is the function which ORs all the possible 8 minterms. And then of course we have the other possibility. So this particular function we have out here is just one of 256 possible functions that exist of 3 inputs. Another way of thinking about it is, if I have 3 inputs, then my truth table has 8 rows. So when I look at the output column, a function is a different pattern of zeros and 1, right? I mean, so how many different ways I can write zeros and 1s in the different rows? Okay, there are 256 possible ways that one would see. So disjunctive normal form is minterms ORed together. As you can imagine, everything has a dual, so there's something called conjunctive normal form. Conjunction refers to AND, so it's basically several max terms which are ANDed together. And this is referred to as product of sums. Product is the AND part, so I'm multiplying or ANDing a bunch of sums, bunch of OR things. So for example, f of ABC being A or B or C, and A or not B or not C, and so on and so forth. So usually the disjunctive normal form is more commonly used, and therefore oftentimes it's just called the normal form. The reason it is more commonly used is because in certain technologies it was fast. The circuit when done with disjunctive normal form was faster, as when it was done as a sum of products was faster, but that's mostly a historical oddity. There's nothing deeply fundamental about it. It's just a lot of things in engineering practice happen because of some weird technological oddity. So if I just call something normal form, it's really referring to the disjunctive normal form, or specifically to sum of products. So why normal form? Normal form of a function is unique because it's just ORing together a bunch of minterms or ANDing a bunch of max terms. The minterm order may be different, but other than that, I can always compare. So given 2 equations, are they equivalent? Well, one way of approaching it is to convert one expression through a series of Boolean transformation into another expression, or alternatively, you convert both of them to the normal form and then check whether they're equal or not. Let's see. So we can sort of compare them. Okay. Look at the thermostat example again. So this was the truth table, and we have a bunch of zeros and bunch of ones. As you can imagine, each one of these rows correspond to a minterm. So what is the normal form of this guy? Well, I can approach this thing so let's kind of work it out. So if I am doing the disjunctive normal form, then the idea is you focus on rows which are 1. because remember we are looking at min terms. So I want to focus on the rows which are 1. There are 6 such rows, and you can say that this function is high whenever any of these 6 min terms that are of interest. So the 6 min terms of interest are this guy, this guy, this guy, this guy, this guy, and this guy. Okay, any one of these 6 is true. One of them. So any given input will result in being one of these rows, and if my input is such that it corresponds to either this row or the bottom 4 rows, then I am good to go. So that's what I have listed out here. So for example, A1 and not A0 and not B1 and not B0 corresponds to the row corresponding to 1, did I mess it up? 1001. So it corresponds to this row 1001, and likewise the others are listed as well out here. And then using our compact notation, I can basically list them as this way. So what this suggests is a very simple way of writing the normal form. I look at the truth table and see which rows are high, and then just OR together the corresponding min terms. So row number 8, row number 9, and row number 12, 13, 14, 15. Very important, you are starting with row number 0, not row number 1. Okay, the first row is always 0. So this basically says M8 or M9 or M12 or M13 or M14 or M15. And that's a disjunctive normal form representation of our system. Even more compactly, I can write it as sigma M, and then within parentheses can write 8, 9, 12, 13, 14, 15. Okay, so this expression, the red expression, the middle expression, and the top expression, they're exactly the same thing. Okay, they're just the bottom 2 are more compact ways of expressing the top expression. So given a truth table, writing the distinctive normal form is just focusing on the rows with 1 and then writing down those particular min terms. For max term, the idea is sort of different. We focus on rows which are 0. And kind of the intuitive idea is the following. So if you think about a max term, so let's look at this max term, A1 or A0 or B1 or B0. This max term is going to be 0 when A1 is 0 and A0 is 0 and B1 is 0 and B0 is 0. All the 4 signals have to be 0 for the max term to be 0, because if any one of them is high, then the max term would be high. So if I'm looking at the very first row, the first row corresponds to the max term A1 or A0 or B1 or B0, and that is 0 when all the 4 signals are 0. So that kind of makes sense that why we are focusing on 0, because if this guy is going to be, if the first sub-expression is 0 when all 4 are 0, then that basically means that I'm really should be focusing on a 0 out here. Okay, so the idea with conjunctive normal form is that look at the rows which are 0 and then jot down the corresponding max terms. So this complicated looking expression, this is basically taking each max term and then ANDing them together. So it's basically saying that if any of these max term is 0, then the function is 0, which is what sort of we want out here. And I can write it down in terms of our compact notation, or I can even write it down as, and here again I messed up, this should be a product. So start with, okay, for conjunctive normal form, start with rows which have an output of 0, and then take the corresponding max term and AND them together. For disjunctive normal form, start with rows which are 1, write the corresponding min terms, and OR them together. Okay, and they give the same function. You can, given this function, you can go to the other one by using De Morgan's theorem. Okay, they are implementing exactly the same function. So Okay, so I'm going to stop out here. We have just a few seconds remaining. So we kind of looked at these two sort of common standard forms in which you can write a Boolean expression. Starting from a truth table, you can kind of go to that, or you can, given a Boolean expression, you can write the truth table, then write the standard form, or kind of go whichever way you want. So again, reminder, no lecture on Monday. I'm going to be announcing a makeup